Hello everyone, good morning. It's a beautiful day. Today I hope you are all well. Today we will start a revision on linear algebra with programming. This course is dedicated for the students in the Cairo campus with Lisbon, with Nova and Lisbon of course. All the course notes, references on Model, I don't have to talk about Model so much. You have everything over there. You have the midterms, some of the previous exams. You have all the course materials. Also, you have recorded vids for all the course, so you can review your stuff whenever, whatever you want to do that. Also, all the recorded lectures for this course is already available on the YouTube channel. My name, Dr. Omar Mohammed. Okay, Dr. Omar Salah, so you can check them if you want to. It's Dr. Omer Salleh. You will find my photo over there like this, and you will get the pyramids behind me. Just go over there, go to the playlist with SPE, and then you will find all the lectures starting from the first one. Talking about this lecture, you will have also some exercises and so on. Okay, let's go through our course notes and how to start reviewing if you didn't do so. So, the very thing that I want you to keep in mind, I will need to arrange my time. I have good time management. I will have to review all the course notes that I've did go through through my study all the year. So I need to, just to remind you, you will have to go through matrices. This is going to be fast, okay, revision, because you already know about matrices, you already know about the operations, you already know about everything. So just to go through them as fast as possible. So going through matrices, properties in all operations, addition, multiplication, multiplication of scalar, multiplication of matrices, the laws, the properties, and everything. You have a bunch of questions, you have a bunch of problems, so you can review them as fast as possible. Second, go to linear transformation and the applications on the Lintov matrix. Also, you will find a complete sessions about this topic, how the application is made, how to apply it, and we already review it before the first midterm and also before the second midterm. Remember what we mean about vector space. It's really important topic. It contains a lot of information. You will need to gather them up, so just to go through them. What are the conditions to have a vector space? It's really very simple. All you have to do is just two things. Be sure that you have an addition closure and homogeneity, or a multiplication by scalar already contained within your vector space as explained in details in these sessions. Also, the conditions for subvector space, which is a subset from a vector space, and the conditions are exactly the same. Addition closure, multiplication by scalar closure, but also sharing the origin or the null vector with the main vector space. Look at the conditions and the formulations and formation of these vectors, subvector spaces. Also, we did go through basis and the coordinates of a vector space, how to get the basis, how to get the coordinates, what's a linear combination, how to link if you have a set of vectors and you're suspecting if they are a basis or not. So you will have to check if these set of vectors are linearly dependent or linearly independent. And this is really very simple. And it is explained in the main materials resources plenty of times. So it's really very good to go through it. Also, through the YouTube, you will have a bunch of vids which contain as a quick revision. I believe the first one was Lintov matrix. By the end of this part, I did a revision on the first midterm or first session, and also you will find a complete revision covering most of the topics that was involved in the second midterm. So you can just review them. They are sufficient from my point of view. And also, if you need more details, you will find all the sessions recorded as I told you previously, and also you will have all the course materials on Moodle. I just want to go quick with you on basis. So if V be a vector space and B is a subset from B, we say that B forms, or this set of vectors, forms a basis for V if you have just two conditions. Number one, the set P of vectors should be generating set of V and also linearly independent. How to check linear independence? Just to check the formula that alpha 1 times u1 plus alpha 2 times u2, blah, blah, blah. If you are in 2 dimensions, so it's going to be alpha 1, u1, alpha 2, u2. And if you are in 3 dimensions, you will have alpha 3, u3 should equal to 0. And this will happen just only this system. If you try to solve it and you ended up having a unique solution, that's alpha 1 equal alpha 2 equal alpha 3, all of them equal to 0, then u1 and u2 and u3, these bases is linearly independent set of vectors. Otherwise, if you have a solution for this values, alpha 1 doesn't equal to alpha 2, doesn't equal to alpha 3, or there is one of them equal to a certain value, or one of them depends on the other, then this means you will have a dependent set of vectors, and which means you can take one of them out if you want to find a basis for your subvector space. Okay. Also remember that the dimension for Rn equal to n, which is simply if you have an R2, for example, so the dimension is going to be 2. If we are talking about R3 or R4 or whatever, so the dimension will equal to the number on the dimension that we are talking about. So if you are talking about 3D, which means R3, so n will equal to 3. Also for the dimension of matrices m sub n, the dimension will be m times n for the dimension of matrices. Of course, it has some special cases. It depends on the formula that's or the conditions that have been given to you in order to make a subvector space. If we are talking about the general case, so it's gonna be m by n. The standard basis, which is the main basis that's forming or the ideal one, also on the normalized form. I think you may heard that previously in the previous sessions. We mean by the standard basis the simplest base that we can use for forming R2, R3, or up to any dimension, which means that you will have a vector, all the elements equal 0 except for I and I. So for R2, for example, if you are seeking the standard set of the standard basis, it's going to be 1, 0, 0, and 1. And this basis will be sufficient to generate mainly any point within your space. If I'm talking about R3, so the basis can be given by just 1 and double zeros, or as you know, 0, 1, and 0, or 0, 0, and 1. And this also set of linearly independent vectors can generate any vector within R3. So it's a very famous and used set of vectors. This is called the standard or the canonical basis for Rn. I'm talking in fast because I want to go through the mock exams or the exams of the last year. I've chosen some of them. All of them are solved already on Moodle, but I chose a couple of them, 2 of them actually, and we will go through them step by step just to tackle the ideas, how to remember them, how to think about these problems. I will go through it. But for the time being, this is mainly just a quick start up for a revision. If any of this is not clear for you, just as I told you several times, go to the main slides or go to the main videos sessions about these topics in details. You will let B be a vector space and be a basis for V if V belongs to V, then there is just only one linear combination of the vectors. So I want you to remember the linear combination, as I told you previously. The linear combination of any vector belongs to subvector space. Let's say U, for example, and if this subvector space, if we call it S, and you just have, for example, U1, U2, U3, which are the basis for S. So any vector can be simply written in a unique manner, which is alpha 1 U1 plus alpha 2 U2 plus alpha 3 U3. You already know that U as coordinate set with respect to S, it's gonna be the set of alpha 1, alpha 2, and alpha 3. This is what we call our coordinates, and it's written here. Let V be a vector space. This is the basis as an ordered set, a basis of V and U. So this scalar value, this is going to be a linear combination for any vector. And the set of these coefficients, which is alpha 1, alpha 2, alpha 3, or in general C1 up to Cn, it's going to form for you the coordinates that you will need to with this basis in order to get any vector you like. Here also it's talking to you about the change of basis in a matrix. Let B be a basis, the change of basis associated to B, the invertible matrix P of B, okay, which columns are the vectors of the basis B, respecting the stipulated order. That's it, as was given to you. Okay, now I will jump to the part of the null row and column spaces. This is a link actually between a lot of topics that we did go through, between the solution of a system of equations, the homogeneous solution, the non-homogeneous solution, the link between them, and linear transforms. So it's linking a lot of things. Also going through vector spaces, it's really very nice and very good, and a lot of information you will find in this part exactly. And I would recommend deeply that you go through it more than once. Okay, now I want to define what we mean about orthogonal complements of S. An orthogonal complement of a subvector space, it is the set of all orthogonal vectors on this subvector space. So if I consider my hand a sub of a vector space and it contains plenty of vectors, we mean by the set of orthogonal complements, it is the set of all vectors that are perpendicular on this subvector space. Exactly like the photo that you can see over here. If S is just a subvector space, consists of all or whatever you want to imagine from vectors belongs to this subvector space. The orthogonal set, which is going to be S, and we will symbolize it by this form, it's going to be the set of all vectors parallel to that vector, and they will share the orthogonal or the orthogonal complement of this vector space. Of course, every plane of R3 passing through the origin is a subspace of R3. What I want to tell you about the orthogonal complement. Let W be a vector subspace, as I told you exactly. The orthogonal complement, it is the set of vectors that belongs to the space where when you check the dot multiplication or the inner product between any vector within your vector space and any vector belongs to the orthogonal complement, you will find the result equal to 0. And this stands for any vector, for every vector belongs to the vector space W. Also, one of the important theories in this part is that the dimension of any subvector space plus the dimension of its corresponding orthogonal complement is going to equal to n, which stands for the dimension of your vector of your vector space. Okay, very good. And also you will find a bunch of problems, examples. It's already written and it's ready for you in this part. So you can review them more than once and you will be in a very good shape. Also, I want you to remember this slide. It's really very important. We have recorded a full session talking about this part. Here, in a solution of a system of homogeneous set of equations, I'm sorry, I want to say this statement also, this slide or this part, as I told you previously, connecting a lot of information together, making them all working as one piece. So he's gathering the information from the vector spaces, sub-vector spaces, with a set of equations, how they are treated all together. So it's really very important, connecting them with the orthogonal complements and giving definition for each and every one of them. And also, we have a new classification linked to the solution of a system of equation, which is really very important and benefitable if you want to go through it. So here, in a solution of a system of homogeneous set of equations, we already know that a homogeneous system means you are solving a system of equation where a times x equal to 0. Okay, where a is the coefficient matrix of the system, x is the vector of unknowns, as you know. So, as an example, if you just want to collect stuff quickly, I will have a, if I'm talking, let's say, for example, for a 3 by 3 system of equations. So a homogeneous system could be like this. If you don't remember, it's gonna be like x1, x2, x3, which is gonna equal to 0. So you have this column, which all of elements equal to 0. This is the coefficient matrix, whatever the numbers are, blah, 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 5, 2, and 6, any numbers. So this is a homogeneous system of equations, as I told you about. Okay, you will have either trivial solution, which means if you succeeded in getting the reduced echelon form for this coefficient matrix, you will have a unique solution. The unique solution will be x1, x2, x3 equal to zeros, and this is a trivial solution. Otherwise, you will have a solution with a vector space of generating set representing relation, or you may have infinite number of solutions, and this is what we know down the road, or just in a few seconds, which is the null space, as we will introduce shortly. Also, if you have a non-homogeneous system, that means you are solving the same thing, same way like, but instead of having zeros, you will have here like b1, b2, b3, any numbers that you that belongs to R, if you are in the real plan, of course. So this general system is going to be ax equal b, where b is the right side of this system of equations, and you know, blah blah blah. If we try to reach the reduced echelon form using, for example, Gauss-Jordan or whatever, you will have the augmented matrix, which is simply also just to check that you are remembering what I'm saying. It's gonna be, this is what we call A plus B. This is the matrix A, this is the column B. So putting them in just only one matrix, which is gonna be like this. If this is alpha 1, alpha 2, alpha 3, any numbers, it will be put here simply. And this is the rest. This is the columns. 1, negative 1 and 2, 2, 3, and 6. This is what we call an augmented matrix, which we symbolize by A and B. So if the rank of A, as we are going to talk, at the rank of A equal the rank of A and B, or the augmented matrix that's formed from your system, so you will have a unique, or you will have a consistent system. So if these values equal to the number of unknowns, you will have a unique solution, which means a consistent, independent solution for your system. If you have RA equal to R augmented matrix, but less than the number of variables, then you will have a consistent but dependent solutions, which means that you will have some of your variables depend, their results will depend on another, and the type of the relation will be, you can get it from the final form of the reduced echelon form. Otherwise, if RA doesn't equal to R of A or B, in this case you will have inconsistent system and you will have no solution for this system of equation. Now for these definitions, this is really important because it's gonna connect it all together. You may be asking about some of them. I maybe need one of these definitions in a multiple choice question or a false or true question, so it had to be reviewed. Okay, let A be M by N matrix. We define that, the null space of A, and denoted by null of A. It is a set of solutions, or it's a set of vectors, such that X belongs to Rn, because if you are talking about 3 by 3, so R3, so if you are talking about a 2 by 2 system, so you are in R2 and so on, blah, 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 such that A of X equal to 0. This is what I'm telling you about. So, a null space, you will get it once you try to solve a homogeneous system of equations, something like this, but with this column all equal to zeros, as you know. Okay, here's your system, try to solve it. Okay, M represents, of course, for an M by N matrix, and M represents the number of equations, and the M stands for the number of unknowns. Also, you have the row space of A, which means your rows one by one. So this is the first row of A, second and third row, and it can be written in the row space, okay, row coefficient matrix. Okay, the column space A denoted by the column of A, and it is the span of a subvector containing the columns of your coefficient matrix, as I told you previously. Also, remark that the orthogonal complement of the rows is equal to null of A. And also, remember, this is what we define about the orthogonal complement, which means if you multiply row of A times the null of A, you will get your set of equations. Here's a simplification. If I have x, y, z stand for the rows, dot R1, x, y, z stand for the general column of homogeneous system of equations, times dot R1, the result will equal to 0, so you will end up having the first equation, second and third. So, makes sense? Okay, this is really very, very important statement. This statement states that N, which stands for the number of unknowns in your system of equations, dimension of null of A is the number of vectors in the homogeneous solution, and it stands for the number of free variables. This is the dimension of null A. Dimension of row A equal the dimension of the rows, number of rows already exist, will equal to the number of columns, and it's equal to the rank of A. This statement is huge, and these comments or propositions already introduced to you previously in your slides. The first remark, N is the number of unknowns. You already know that. Dimension of null A is the number of free variables. So once you try to solve a system of homogeneous equations and you end up the final step or the final state for this infinite number of solutions, I want you to remark that the dimension of null of A is the number of free variables. It means the number of 0 rows in your reduced echelon form. So if I'm starting a 3 by 3 system of equations, and once we are trying to get to the reduced echelon form, you ended up having just only one row equal to zeros from the beginning to the end of your augmented matrix. This means the dimension of the null is 1. Okay, if you have a couple of rows equal to zeros, for example, so the dimension of null A is going to equal to 2, and so on. So each row, each complete row that's really exists in your augmented matrix, once it is a square matrix, number of unknowns equal to number of equations, it will stand for the number of free variables. So it's stated here, dimension is the number of free variables, or 0 rows in the reduced echelon form in the infinite system if exists, if you are dealing with an infinite system. Dimension of row A is the number of equations in the system of equations. Dimension of column A is the number of unknowns in the system of equations. Rank of A, as defined, there's a difference between the number of unknowns and the number of free variables, okay, or the 0 rows, the number of 0 rows. Okay, Let A be a matrix. Let A be a matrix. Let A be an M&N matrix and be a matrix in the echelon form row equivalent to A. So once you start with A trying to get to the reduced echelon form, this is equivalent to it. The non-null rows of V as vectors of Rn form a basis of row of A. This is very important statement. Okay, the columns of A as vectors of Rn corresponds to the columns of B with pivot from a basis of column of A. Okay, these propositions, as I told you, the dimension of the row A plus dimension of the null of A should equal to n, and that statement is related to the main statement which states that any dimension of a subvector space and plus its orthogonal complement, the sum of them both together will equal to the dimension of your vector space. Because as I told you, I'm explaining this, and you will find that in the many slides explained in details. So it's the dimension of row A plus the dimension of the orthogonal complement of A will equal to n, and this is also the relation that we used. Let A and B n by n matrix, and X belongs to Rn, then Ax belongs to the column of A. That's the reduced product of A with the corresponding matrix. You had previously illustrative examples on the main slides on this topic. We can conclude that Ax is always a vector in the vector space of A, as it is a linear combination of A columns. Also, these statements will end you up with rank of A equal the dimension of the column equal the dimension of row of A. The rank of A equal to the rank of the its transpose. Okay, this scheme, it's already exists in your resources, main resources on your on the model. Also, it will be involved. It's gathering most of the information that we talk about. Any solution set of a system of equations, it will consist of two parts for the three types of solutions of a system of equation. The first of them is XP, which is the particular solution once you are dealing with a system of non-homogeneous equations, plus null of A is a solution of the homogeneous system of equation. Of course, B belongs to the column space of A because P for a system which is Ax equal P should be it will be a column which is exactly corresponds to one of the columns of the coefficient matrix. Okay, which means that for this condition to happen, you will have a consistent F, a consistent solution, either consistent dependent or independent for this condition. Okay, if inconsistent F, or you will have inconsistent system if the B doesn't belong to the column of A, which means B, the column, the end of your reduced echelon form belongs to R4 plus and the column of your reduced echelon form belongs to R3, for example. So they are not, dimension is going to be 4, this is going to be 3. They're not going to equal to each other, which means you will have an inconsistent system of equations. But if you ended up in a reduced echelon form having here a dimension of 3 and also dimension of columns equal to 3, both of them equal to each other, you will have consistent system. Either if it was a consistent independent solution, and this will happen only if the dimension of the null of A equal to 0, so you don't have a complete row equal to 0 in your system. Okay, so the solution will be XB. You will have a consistent independent solution. Otherwise, if you have any value for the dimension of the null of A, which means dimension is greater than 0, you will have a consistent dependent system of equations. This is really very important scheme, and you will find it in your main resources or your main slides, and also explained in the videos on model, and explained also in the recorded lectures previously. And also you will have a lot of examples solved about this part. both in exercises and both in the main slides. We will let A be a square matrix of order m. The following statements are equivalent. Usually, when we find some slides like this, gathering some information about or comments, propositions, or lemmas, please try to read them carefully, because you will be subject to questions about this, or some of the problems or some of the ideas involved in your exams will be covered or will be within these remarks. So rank of A is equal to n. A is invertible. A is equivalent to a unit matrix. So once more, let A be a square matrix of order n. The following statements are equivalent to each other. If I have AX equal B is a consistent independent system, that will happen for every B belongs to R of N, which means that the B column should belongs to or should be the same dimension as the column space of the coefficient matrix. Column A equal row A equal Rn. Null of A equal to 0. This is a condition for having a unique solution. So it's actually equivalent to all of this. Rank of A equal to the number of unknowns equal to the number of equations. So you have a consistent independent solution. Once you have this, the matrix of the coefficient matrix will be invertible, because you will have a value of the determinant, as you know, down the road, and it will be invertible. A can be reduced to, if you are trying to get a reduced echelon form, you will succeed in reaching IN. And of course, the other statements are clear. The rows of A as vectors of Rn form a basis for Rn. The columns of A as vectors also form a basis of Rn. Because simply, if you start your problem trying to get to the reduced echelon form, you started by 3 by 3, for example, and you will end it by an unit matrix 3 by 3. What I want to clarify that all of these statements, for example, talking about any problem like 3, 6, 2, 5, 2, 1, 0, negative 1, and 6, and you will have 7, 8, 100, whatever. This system, if you succeed in getting it into the reduced echelon form, which is simply gonna be 1, 0, 0, 0, 1, 0, 0, 0, 1, and whatever the numbers that you will get here, let's say P1, P2, B3 for numbers. Okay, if you look at this final form, if you look at the beginning, this is, of course, your matrix from your system of equations, your invented one, and this is the last form. All the remarks here are based on this case, so it's all equivalent to this case. So, first of all, rank of A equal to n. Yes, number of non-zeros equal to 3, and the number of the unknowns equal to 3, so they are equal to each other, so it makes sense. Okay, very good. A is invertible. Of course, A is invertible, since you succeeded in getting a unit matrix. Of course, I didn't do the steps. I'm just clarifying if it works like this. So, once you get a unit matrix, that means the determinant of the coefficient matrix, the determinant of this part will never equal to 0, which means it is invertible. A equivalent to IN, this happened already by the reduced echelon operations or the row operations in order to get to a reduced echelon form. AX equal B, as I told you, B belongs to Rn. This is the column space, all of them are R3, and also B1, B2, B3 belongs to R3, so it's correct. And null of A equal to 0, the solution of this system, if it was homogeneous, so 0 is over here, the solution would be 0. So 0, 0, 0, which means U belongs to the null space. The row of A as a vector of Rn form a basis of Rn. In fact, yes, exactly right. Here we go. And also for the columns. Proposition, let T, we are talking about a linear transform from Rn to Rm, be a linear transformation. Then remember that A map T from Rn up to Rm, it can be written as a matrix times X. Remember also, and the similarity with A of x, the kernel of T is similar to null of the A, and the n minus n, also this identity we already talked about, the dimension of row A plus dimension of null equal to n. Of course, remember that the range of T of a linear transform equal to the column of the linear transform. Okay. Dimension null dimension columns equal to n, and since dimension of kernel equal to the dimension of null of AT, this is all statements that we did go through it. Dimension of a kernel plus dimension of a range equal to n. We checked that previously in the linear transformations. T is injective. Remember, T is injective. If and only if the determinant, the dimension of the kernel equal to 0, and it is surjective if and only if the dimension of ker T is equal n minus m, and we also can say that it's surjective if the codomain, okay, is covering the whole dimension, the images of U transform covering the whole codomain. Okay, perfect. Now I want you also to remember the determinants and its applications. It was not really covered in details in the second midterm. We did go through determinants as fast as possible while we were studying this part. So I would deeply recommend that you go through them once again, the properties of the determinants, which the most important bunch of them is let A be a square matrix of an order n. We say that the determinant of a matrix A denoted by determinant A, or just having the modulus symbolization of A. It is the real number, stand for if you have a 1 by 1, so it's going to be equal to this number. So if I have a 1 by 1 matrix, let's say 1 by 1 matrix may stand for something like this. A matrix with 100, for example. So if it was A, so the determinant of A will equal to 100. This is for that statement. Okay, if n is greater than 1, we will use